In this video, I will provide a short introduction to data analysis for ordinal scale data. And I'll also demonstrate a couple of different calculators that are available online that can be used to perform some of these different types of analyses. So first, let's talk about some of the characteristics of ordinal data analysis techniques. So when we think about ordinal data, we're thinking about data that is a rank, similar to what could be found in a Likert scale type of a survey question like satisfaction or agreement level. And that's typically the type of data that we're using here. And so this type of data does not or cannot have a true mean or standard deviation calculated. So because of that, for an individual Likert scale type of a measurement, we cannot use t-tests or ANOVAs because typically that data does not meet the assumption of a t-test or ANOVA. And so because of that, we need an alternative. So we can use these ordinal data techniques to measure things that might be a little less objective or maybe a little less quantitative. In other words, they're not interval or ratio scale. They might be ordinal scale data like ranks. Now, if we have interval or ratio that is skewed, in other words, it doesn't meet the assumption of a normal distribution, then we can also use these ordinal data techniques to analyze that type of data. So very often interval or ratio scale data that is naturally skewed, we can still analyze that data. And so what these formulas do is take that interval or ratio scale data and convert it into a rank, convert it into ordinal scale, and then it can be analyzed. So this is a process in which we have data that's a little simpler. If we've got interval or ratio scale data that might have very large numbers, it might be easier to convert that into a rank. So when the assumptions of inferential testing or parametric analyses is violated, such as what we might see in t-tests or ANOVAs, we have an ordinal data alternative. And then very often when we have scores that aren't very objective, in other words, it's very difficult to determine true intervals between potential scores, like we see with agreement or satisfaction, then these interval data techniques are a good alternative. So let's talk about some of the different tests, and we'll demonstrate each of these as we talk a little bit about their theory. So the first one we're going to talk about is the Mann-Whitney U Test. And this is where we're comparing ordinal scale data from two separate or independent groups. So this is an alternative to the independent t-test. So the idea is the same as we have with an independent t-test. We have two groups, treatment versus control, male versus female. They're independent groups, and we want to compare them on a single outcome score or variable. And so this would be analogous to the independent t-test. And so if we violate the assumptions of an independent t-test, then we can use the Mann-Whitney U. The Wilcoxon test is a repeated measures test. So now we have two different treatment conditions. So this might be a pre-test, post-test type of a design, or this might be a crossover design in which we have the same subjects receiving two different treatments, and we're measuring their response to each of those two treatments. So this would be the alternative to a repeated measures or a dependent samples t-test. Same people being measured twice. So again, if we violate the assumptions of the dependent samples t-test, we now have an alternative in the Wilcoxon. And then the last one we'll demonstrate is known as the Kruskal-Wallis test. And this compares data from three or more independent groups. So again, if we've got three different treatment groups and we want to compare them on a ordinal scale outcome or on a skewed numeric outcome, and this violates the assumptions of the one-way or single factor ANOVA, then the Kruskal-Wallis is an alternative for that. So you can see how these three tests have analogs or have are analogous to some of the parametric tests we talked about already, the t-tests and the ANOVA. So if we have data that doesn't fit those criteria to do those tests, then these are our three alternatives. So let's talk about the Mann-Whitney U test first, and then we'll go ahead and demonstrate a calculator that can be used to calculate this kind of test. So again, this is used to evaluate the differences between two treatments groups or two different populations, or maybe two different samples from different populations. And so it works with the following logic. And so the data becomes ranked. We take the numeric data, we list it all from highest to lowest score, and then that score is applied a rank. Or maybe the data already is a rank, and so we order that from highest to lowest rank, however you want to frame that. And so what the formula will do then is look for differences between the rankings of our two groups. So if we have one group that tends to concentrate more towards the higher end of the rankings, and the other group tends to concentrate more towards the lower end of the rankings, then that indicates there's a real difference between those two groups or those two sets of scores. If there is no difference in the distribution of the rankings between the groups, so if there's a kind of a random distribution of rankings for people in group 1 versus group 2, then there's no difference between the groups. And so that is typically the null hypothesis, is there will be no difference in the distribution of scores among the rankings. So to give you an example you might be able to relate to, if we have two different teams, two different track teams that are both running in the same race, and we want to test to see if if one team is better than the other team, if they're going to have a better finish than team B. And so if team A is better than team B, then most of their athletes are going to finish in the top rankings. They're going to finish first, second, third, fourth, fifth. And then if team B is not as good as team A, then their athletes are going to finish the lower rankings. They're going to finish 15th and 16th and 17th and 18th. So when we have that kind of separation in the rankings between two sets of scores, that indicates a difference between those groups. And so the Mann-Whitney U Test is able to pull out those potential differences. And again, going back to the null, if those two track teams are equal, they're just as good as the other, then those individual track athletes from the teams will be distributed equally in those rankings. Someone from team A might finish first, someone from team B finishes second, someone from team A finishes third, and so on. So we get that even distribution. And so that's what the formula will help us determine, if there is a difference between those two groups. So let's go ahead and see a demonstration of how this is done. So we're going to go back to the same website we used for our chi-square test, and here we'll be able to do the Mann-Whitney U test. And so if we look at our menu here on the left, we can see there's a Mann-Whitney U value calculator. So we go ahead and click on that, and it's going to explain a little bit some of the requirements and some of the assumptions or criteria for doing a Mann-Whitney U test. And it's also going to give us the formula so you can get a sense of how this process works, of how the formula actually works. So as we go into the calculator, you're going to be asked to enter in the data for your two groups. And so how we do this, the easiest way to do this is you can attempt to copy and paste in. It might depend on, it might vary how the data gets pasted in. But if you're going to enter by hand, you'll need to enter in your value, hit the enter key, and then enter in your second value. So let's say we have some data here on student satisfaction. So how satisfied students are with their experience in taking a statistics course. And we want to see if there's a difference between two different instructors teaching the same statistics course. So population 1 or group 1 will be the group that's taught by teacher A, and then population 2 or group 2 is the group of students being taught by teacher B. They're teaching the same class using the same materials, but we want to see if there are differences in how satisfied students are with these two different teachers. So we have rank data here. We've got data that can range between 1 and 5. So a 1 would be very unsatisfied and a 5 would be very satisfied. So each student is going to rank themselves or rank their satisfaction, and then we're going to compare the two groups to see if there are differences in their satisfaction ranking. So I'm going to go ahead and enter in the data here. So as you can see, I've entered the data, and it doesn't matter what order you enter the data in. You can enter the data in whatever order, because the calculator will reorder it or rank it for you, so you don't have to worry about putting it into a rank order. So as you can see here, we've got the responses, the satisfaction responses for group number 1, and then the satisfaction responses for group number 2. The next thing we need to do is tell the calculator at what significance level we wish to test the null hypothesis. And again, our null hypothesis is going to be that there will be no difference in the distribution of ranks between our two groups. We can then choose the tail of our hypothesis test, and typically we're going to choose a two-tailed hypothesis test because we don't know what direction the differences might be. Will group 2 be higher than group 1 or group 1 higher than group 2? We don't know that, so we select the two-tail. Once we have our data entered in and we've selected our two options here, we go ahead and click Calculate U. Okay, and so as we page down here, it's going to give us a couple of different outputs. The first is going to be the actual U value, and a U value of 50. And so what the formula does then is convert that U score to a Z score. And when we have a large enough sample size, usually more than about 8 subjects, U values represent or can be represented by a Z distribution. So we can actually use the Z-score, a Z-score, to then make our hypothesis decision. And so you can see the Z-score here is a 2.1. And so that equates to a p-value of 0.029. Now that is less than 0.05. And so we're going to be able to reject the null hypothesis and say that there is a significant difference between the two groups. In other words, one group had a much higher or much lower typical ranking compared to the other group. So there's a separation. Now we can report this as median score. So we can then calculate the median score for group 1 and the median score for group 2. And that's how we do our descriptive reporting for our two groups. And then depending on what the median score is for each group, we can then see where the real difference is. Does group 1 have a higher median score than group 2? So in this case, we have a significant difference between our two groups, with one group having a much higher median rank or median score than the other group. And so we could make that conclusion that there are significant differences between our groups. Okay, so that's how the Mann-Whitney U Test and the Mann-Whitney calculator will work. Now let's talk about the Wilcoxon test, known as the Wilcoxon Signed-Rank Test. Now, as we mentioned before, this is the alternative or the analog to the dependent samples t-test. So we're comparing, again, ranked scores or ordinal scale data from related groups. So it's the same group of people being measured twice, either in a pre-test, post-test design or potentially in a crossover design. So when the assumptions for the dependent samples t-test are violated, this is our alternative. So again, we're using data that is either truly a rank score, truly ordinal data, or it could be numeric data that's then converted into ranks. And it creates a test statistic called the W statistic. And this also has a distribution that mimics the Z distribution. Again, if we have more than around five or six, depending on who you read, between 5 and 8 subjects, if we have more than that, then we typically can use the Z statistic, and we can make our hypothesis decisions based upon the Z distribution. So the Wilcoxon Signed-Rank Test uses the following logic. It looks for the direction of change for each pair of scores. So it takes each pair representing one individual and looks to see how much the scores or the ranks change from time point 1 to time point 2. And so it either assigns a plus or a minus as far as the direction of change, and then it gives it a value, a score that indicates the magnitude of change. Did you change by 5 points, 10 points in a positive direction or a negative direction? So if we have a lot of positive signs among our pairs of scores, then that indicates a decrease from one observation to the second. If we have, and again, what the formula thinks of is if we have a rank of 1, that's the best score, and a rank of 3 would be a lesser score. We think of like finish place in a race. If you finish first, you have a rank of 1, that's better than a rank of 3. So that's why when we have that decrease, that's where we get a positive sign. A preponderance of negative signs would suggest just the opposite, that the ranks are going up. So the null hypothesis then is that there is no tendency in either direction. The numbers of positive and negative signs will be approximately equal, and the magnitudes will be approximately equal as well. And so when that happens, we expect to have a value of W to be around 0. And so we would be able to accept the null hypothesis and say that there is no difference between time point 1 and time point 2. So that is the basic logic behind the signed rank test. So now let's go ahead to the calculator and we'll see how this will actually work. So now we're back to that same website we were at previously, and now using our menu, we've chosen the Wilcoxon Signed-Rank Test. And again, it gives us a short overview of what the test is designed to do and what are some of the parameters or some of the conditions for using this test. Again, matched data, pre-test, post-test kind of design. And again, we're comparing the medians of the two samples, and the idea is that the median rank or the median score is going to be identical. That's our null hypothesis. So in order to use the calculator, it's going to look a lot like the Mann-Whitney U interface did. So we're going to enter in our two sets of scores. So this might be the set of scores for the pre-test, and this might be the set of scores for the post-test. So I'm going to go ahead and enter in, again, some data. And let's go ahead and continue with our example that this is satisfaction data. So let's say now we have a group of students who we're measuring their satisfaction in their course, and then we're going to make a change in that course in some way, change the instruction or change the textbook or location or whatever, and then we're going to remeasure their satisfaction. So we've got a pre-test, post-test, same group of students being measured twice. Satisfaction before a change in the course, and then satisfaction after the change in the course. And we want to see if there's a statistically significant difference in their satisfaction before and after the change. So now the data I've entered is using that same 5-point scale, with 5 being very satisfied and 1 being very unsatisfied. And so now we want to see if there's a difference in satisfaction from time point 1 to time point 2. We need to make the same kinds of choices, the significance level we wish to test at, and then the tails of the hypothesis test, two-tailed versus one-tailed. Again, I don't know if satisfaction scores are going to go up or they're going to go down, so I want to test using a two-tailed hypothesis test. Remember, our null hypothesis at this point is that there will be no difference between the median ranks between the two time points. So we'll have it go ahead and calculate. And again, it's going to give us a lot of information here. It's even going to show you the ranks. It's going to show you the change between each pair of tests or each pair of values. And it's going to give us our W value. And then here is the Z score associated with that W value. Now, as you can see here, our sample size is 14, so we can go ahead and use the Z-score to make our hypothesis decision. A little further down, it's going to tell us the Z-score, minus 2.82, and that's associated with a p-value of 0.0048. So that is much less than 0.05, so we're going to be able to reject the null hypothesis, and again say there is a significant difference between the two measurement points. Again, I'd have to calculate the median score for each group of scores to make some sense out of that, what that actually means, if the values went up or down, and by how much. But there is a significant difference here. So I can reject my null hypothesis and say that there is a significant difference from the pre-test to the post-test, and conclude that whatever the treatment was or whatever the intervention was has changed the scores at a level that goes beyond just a chance change in score. Okay, so that's how the Wilcoxon Signed-Rank Test works. Now let's talk about our third test, and that's the Kruskal-Wallis test. So the Kruskal-Wallis test, as I mentioned, again, is a non-parametric test in which we want to compare 3 or more groups of data. So this is used when the assumptions of a one-way ANOVA are not met. So much like the one-way ANOVA, in which we're comparing 3 or more groups on a single numeric outcome, with Kruskal-Wallis we're comparing 3 or more groups using either ordinal data or skewed numeric data. So again, data will either take the form of a ranking in its original form, or will be data that can be converted to a ranking. So the logic works pretty much the same as the Mann-Whitney U Test does, except now we have more than two groups. And so again, we're comparing group medians and we're using ranked data. And so the formula looks for a difference between the distribution of rankings. And so if we have groups of scores that have a greater concentration, Group A has a greater concentration at one level of ranking versus Group B, and then versus Group C, then we're going to see significant differences. If there's no difference in the distribution of scores, then there's no difference between the groups, and there we've met our null hypothesis, where we can accept our null hypothesis. Now, much like the one-way ANOVA, if we find significant differences in the initial analysis, then we're going to be able to do post-hocs. So we can actually do those pairwise post-hoc comparisons, much like we did with one-way ANOVA. And we don't have a built-in post-hoc test for Kruskal-Wallis, so what we end up doing is doing a Mann-Whitney U test for each pairwise comparison. So if we see significant differences, we want to do a Mann-Whitney U comparing Group A to Group B, and then Group B to Group C, and then Group A to Group C. And again, much like we very often have to do with a one-way ANOVA, we might need to do a Bonferroni correction to correct our p-value for our post-hoc so we don't get an inflated error rate. So if we end up having to do post-hocs, if we have significance initially, we want to make sure we do that Bonferroni correction. So if we've got three groups that we're comparing using the Kruskal-Wallis and we find significant differences, we're going to do three pairwise comparisons. And so we need to take our p-value of 0.05, if that's how we're initially testing, divide it by the number of pairwise comparisons, in this case 3, and that gives us a new p-value of 0.017, and that's the p-value we would use for our post-hoc comparisons. So now let's go ahead and see how this would work in one of the calculators. So this calculator comes from a website that's different than what we've been using previously, but I found this to be one of the easier ones to use. And again, at the top it gives us a quick description of how this test can be used and when it should be used. And we're going to see some of the same data windows. So let's continue with this example of using our student satisfaction scores. So let's say now we've got three different instructional techniques we want to use to teach statistics. And so we want to compare the satisfaction scores from students using each of these three different techniques. And so each group of students is independent, each getting a different teaching technique. We want to see if their ranked score of student satisfaction will differ among our three sets of scores. So I'm going to go ahead and enter in some data here. So here I've entered in data for our three groups. So we've got Group 1, Group 2, and Group 3, each receiving a different instructional technique, and we've got their ranked data. So again, a 5 is very satisfied and a 1 is very unsatisfied. So once we have our data entered in, we then need to enter in which p-value which to test this null hypothesis, that there will be no difference between our three groups. We need to enter in that p-value, and we're going to test at 0.05. And then once we have that entered in, we go ahead and click Solve. And so it's going to give us a lot of output. I'll page down here fairly quickly. It gives us a fair amount of output, and you'll see this when you try it. So it organizes the data in one column so that it can be ranked, and then you'll see how it's ranked it, and then it assigns ranks organized in order. And it's interesting to be able to see how the process works, but you're more interested in what's happening down at the bottom here. So down here it's going to give you a critical value for this particular test. And again, the Kruskal-Wallis test uses a z-score distribution, actually uses chi-square and uses that distribution. And so the critical value for this particular test, because we have a p of 0.05 and the degrees of freedom of 2, the critical value for this test is 5.991. Now the next thing we can look at is the actual h value or the actual Kruskal-Wallis value, and that's 3.053. Now that is less than 5.991, so we will be able to accept the null hypothesis and say that there is no significant difference. Now we can double check that and look at the p-value associated with that h value of 3.05. And that's a p-value of 0.21. That is greater than 0.05. So that just reinforces the idea that we have to accept this null hypothesis and say that there are no significant differences between these three groups. So at this point we can stop. Post hoc tests aren't necessary, and we can say that the three different teaching techniques have no effect on student satisfaction. The level of student satisfaction is equivalent among these three groups. There's no difference. Now, if we would have seen significant differences, then we could have moved on and did our post hocs. But in this case, because there is no significant difference, we can stop here, accept the null hypothesis, and say that there is no significant difference. So to summarize, what we've done is looked at three different very common techniques we can use to analyze ordinal scale data. We use some online calculators to perform these analyses, and I will put the website addresses for these calculators in the description underneath the screen in the video, so you can just click on those and follow along as you go through the video. So these three different techniques can be used as alternatives to parametric techniques, the two t-tests, independent and dependent t-test, and then the one-way ANOVA. So if your data does not fit the assumptions of those three tests, you do have an alternative so that you can do group comparisons. So hopefully you found this video useful, and good luck using